Warm good evening to one and all present here. Myself, Dr. L. Kumar, coordinator of this event and working an associate professor in mechanical department in Jansen's Institute of Technology. First of all, I like to thank and welcome all participants and my dear friends. I am here to deliver the agenda for today's session. First, the session starts with welcome address. It is delivered by Mr. Daniel from Final Year Mechanical. Second, chief guest profile unveiled by Mr. Ashok Kumar, Final Year Mechanical. After that, the session is handover to our esteemed chief guest, Dr. Ajith Kumar K.K. At the end of the session is allotted for discussion. After the discussion got over, vote of thanks is delivered by Mr. Sanju Vishal from Final Year Mechanical. After that, we are allotted discussion session. You can ask any questions on that section. After completion of 45 minutes, we can send the feedback link through YouTube chat box. After filling your feedback form, you get a certificate within 2 days. These are today's agenda. Now I call Mr. Daniel to present welcome address. So Daniel.
Thank you, sir. A very good evening to one and all present here, to our esteemed management, respected CEO Mr. Mohan, beloved principal Dr. V. Naharajan, honorable chief guest Dr. K.K.Ajith Kumar, distinguished head of mechanical department Dr. M. Muthukumaran, faculties and dear participants. It gives me immense pleasure to extend a very warm welcome to all of you present here on behalf of the Department of Mechanical Engineering. I would also like to express our gratitude to our esteemed chief guest, Dr. K.K.Ajith Kumar, who has accepted our invitation to deliver a speech immediately for this webinar on his busy schedule. To make the seminar interesting, we have picked fresh and emerging topic and an eminent key speaker to the participants involved engage, discuss, and share their thoughts. I'm sure that you will all feel enriched with knowledge in metal processing and characterization after completion of this webinar. I welcome you all once again to the webinar and hope that you will have a great time ahead. So now I hand over this section to Ashok Kumar to deliver unveil the chief case profile. Thank you very much.
Thank you, Daniel. Good evening to one and all present here electronically. It's my privilege to unveil about Dr. K.K.Ajith Kumar. Dr. K.K.Ajith Kumar accomplished his bachelor degree in mechanical engineering in 2005. He finished his master's in engineering design in 2007. He completes his Doctor of Philosophy in School of Mechanical Sciences, Indian Institute of Technology, Bhubaneswar, and Material Science and Technology Division, CSIR, National Institute for Interdisciplinary Science and Technology, Thiruvananthapuram, Kerala, in 2014. His PhD thesis title is about processing, properties, and modification of magnesium silicon alloys. His research is about magnesium alloys and magnesium matrix composite, alloy design and development, solidification, material characterization, and nickel-based superalloys. He also completed a postdoctoral fellowship in a GE India sponsored project titled Microstructure Evaluation and Structure Property Correlation for Nickel, Titanium, and Iron-based Alloy System in Department of Metallurgical and Material Engineering, IIT Kharagpur, India from November 2014 to June 2015. He is well skilled and experienced in material processing, mechanical and tribological characterization, material characterization, and computer proficiency. He worked as a project assistant grade 3 in DST India sponsored project titled Development of Mono and Discontinuously Reinforced Magnesium Metal Matrix Composite for Engineering Applications in Material Science and Technology Division, CSIR, NIIST, Thiruvananthapuram, India, from December 2012 to March 2013. He worked as a Senior Research Fellow in Materials and Minerals Division, CSIR, NIIST, Thiruvananthapuram, India, from November 2008 to November 2012. He worked as a Project Assistant Grade 3 in a ARDB India-sponsored project titled Development of Magnesium-Based Alloys for High Temperature Applications in Materials and Minerals Division, CSIR, NIST, Thiruvananthapuram, India, from December 2007 to October 2008. He worked as an assistant professor for 2 years and associate professor for 2 years. He guides 3 PhD candidates. He published 15 articles in well-esteemed journals with good impact factor. and also he published 15 articles in conference proceedings in various prestigious institutions like IIST, IIT Madras, and IISc Bangalore, etc. He is a member of IIM, IIF, and MRSI. He is awarded as a Senior Research Fellowship by Council of Scientific and Industrial Research, Government of India from 2008 to 2012. He is awarded as a postdoctoral fellowship by Indian Institute of Technology, Kharagpur from 2014 to 15, and he is awarded as Professor Brahm Prakash Best Ph.D. Thesis Award from Indian Institute of Metals, Trivandrum chapter for the year 2014 on 28 January 2017. Now he is the CEO of MatRICS, that is Materials Research and Innovation Centric Solutions, located at Kanyakumari District. Now I hand over the session to our esteemed chief guest, Dr. K.K.Ajith Kumar. Please, sir.
Thank you, sir. Thank you, Johnson Institute of Technology, Coimbatore, and the Department of Mechanical Engineering for the wonderful opportunity given. That is, today our topic, that webinar topic is research on metal processing and characterization. I'm very much thankful to the all faculties, participants, and students, and especially the convener, Dr. M. Muthu Kumaran, and Professor and Head, and Dr. L. Anuj Kumar. Thank you, Anuj Kumar. Today, before going to the topic, just a brief explanation about the MatRICS. MatRICS is a material research and innovation centric solution. This industry we developed in the scheme of NEEDS, that is New Entrepreneur Come Enterprise Development Scheme, project titled Metal Processing Workshop for Advanced Research. This industry is for young researchers who is doing PhD and other research program, and the project scholars, they can utilize the facilities and they can develop the material. For the reason we developed this MatRICS industry. So we can go to the topic. Our today topic outline is current scope of metal research, type of materials and alloy and composite, metal alloys, metal matrix composite, and what are the different processing steps are there, how the metal is processed from smelting to advanced.
Dr. Ajith?
Yeah.
Kindly press F5 with presentation PPT.
Okay.
Okay, thank you. Full screen mode.
Okay. And the processing of metal matrix composite, what are the different light elements are there, where we are going to use that light elements, what are the different light metals, and different light metal category, what are the different structural materials are available in the industry, and why we are using the light metals, then magnesium and its alloys. After that, the session is about metal characterization, mechanical properties, and summary. So before going to the topic, we need to understand these four different key parameters, that is processing, structure, properties, and performance. We can classify this processing and structure is material science, and properties and performance is materials engineering. So every processing means, we know the processing means metal casting or powder metallurgy, pressing, punching, all are different metal processing method. With respect to processing method, we can change the structure. So every metal, if you see, every metal, we have different microstructure or macrostructure, or in atomic level, that structural property is varying. So that structural property is always with respect to its processing, how we are processing. With respect to that, the structural property is changing. Again, the property. So property is always depends on structures. So how the atomic structure, how the bonding, how the microscopic level structure, how it is embedded with the particle, with respect to that, the property can change. So every engineer always used to select the metal with respect to its property. What property they are expecting, with respect to that, they used to take the, or they used to select the material. So these four key parameters is important. So with these four key parameters, the entire session is always uh, goes with these four parameters only. Because each and every parameters, if we vary, how the mechanical properties we are changing, how the processing method changing its structure, that we are going to see in the entire section. And for the example or case study purpose, I'm using some of my PhD work and some of my papers work in this entire talk. So we can classify metals into three different categories, materials into three different categories, that is metal, ceramic, and polymer. So if you mix, that means a composite is composed of two or more individual material that come from category like metal, ceramic, or polymer. So if you add some ceramic particle into the metal matrix, so we used to call it metal matrix composite or MMC. Some metal particle to ceramic matrix, then it is ceramic matrix composite. Some of the researchers, they used to add small amount of metal powder to the polymer, then that kind of composite is called polymer matrix composite. So with the compost effect, we are changing the matrix composite. So metals, in the periodic table, if you see, about 76 of them are metals. So if you define metal, means it will vary with respect to the profession. A chemist calls the element of a metal if its oxide dissolved in water gives an alkyd solution, then they used to call it as.
Ajit,
Hello?
Ajit sir, kindly pause your presentation.
Okay.
Wait for 30 seconds.
Okay.
Okay. Ajit,
Yeah.
now you proceed. Thank
Okay.
you. Thank you.
Okay. So, defining of a metal, so it will vary with respect to different profession. A physics based on how the metal is means good good electrical conductivity of the element with degrees with the increase of temperature as a criterion to call it as metal. So metallurgists used to tell this is if you add some element or some particles, how the material properties or metallic property is changing, how we are controlling the composition. With the controlling of the composition, how we are changing the structure, then that is called metal, like that he used it. But in the case of engineer point of view, how we are utilizing that substance or how we are utilizing the particular product and what it is made up of. So he always think about what is the use of that, what is its property. With respect to its property, he used to call it its metal or something. So, in general case, metal is any class of substance characterized by high electrical and thermal conductivity, as well as by malleability, ductility, and high reflecting of light. So in recent trend of research in metal, if you see last 3 years from 2018 to 2020, about 5,000 papers, minimum 5,000 papers coming every year in all the basic structural materials like ferrite, lead, aluminum, copper, magnesium, nickel, likewise. In case of ferrite, even though about a long journey of material research, again the ferrite is coming number one position, that is about 20,000 papers are coming every year. And if you see in the processing wise, machining, smart materials, metal matrix composite, pressing, casting, welding, powder metallurgy, or forging case, so about 10,000 papers, 10,000 high-end impact factors papers are coming every year. So all the area, the research ground is open to all the researchers, and moreover in the casting area is about 12,000 papers are coming every year. So we can classify the metal into two different categories. One is alloy, another one is composite. Alloy is a metallic solid formed by an intimate combination of metal or more than one metal or non-metal, but it has metallic properties. Composite is a material, at least two constituent parts, one being a metal necessarily, the other material may be a different metal or another material like ceramic or intermetallic material. Generally, alloys can be either homogeneous or heterogeneous mixture, but always the composites are always heterogeneous mixture. We can see in the picture, in the composites, some black color particles are there. That particles are reinforcement. The gray color region is matrix. So always in the composite, a different particle or hard particle embedded with the soft matrix, that kind of mixture will be there. Then if you classify metal into, we can classify metal into two different categories, that is ferrous and non-ferrous. Ferrous means the main constituent of the material is ferrite or iron. In non-ferrous, other than ferrite is the main constituent, then we can call it as non-ferrous metal. So ferrous we can classify in two different categories that we know, steel and cast iron. Steel we can classify into two categories, that is low alloy steel and high alloy steel. And in the low alloy steel, that is low carbon, medium carbon, and high carbon steel is there. And the high alloy steel we can classify as tool steel and stainless steel. The stainless steel, about 11% of chromium will be there. In the case of cast iron, that we can classify into gray cast iron, ductile cast iron, white cast iron, malleable cast iron, and compacted graphite cast iron. So in other side, non-ferrous alloys, that means we already discussed that if ferrite is not a main constituent, then we can call it non-ferrous alloys. Aluminum alloy, copper alloy, magnesium alloy, titanium alloy, refractory metals, super alloys, noble metals, nickel alloys, lead alloys, tin, zinc, and zirconium alloys. These all are the different non-ferrous alloys. So again, if you come into the metal matrix composite, we can classify into two major categories, that is ex situ composite and in situ composite. So we know the composite is a material with at least two constituent parts, one being a metal. So in the ex situ composite, we are adding the reinforcement externally. That means we are adding silicon carbide particle or boron carbide particle or titanium carbide particle to the aluminum matrix or liquid aluminum melt by stir casting or some other. So we are adding the reinforcement directly, and externally we are adding and mixing, we are making the ex situ composite. But in the case of in situ composite, we are adding some salts or some reacting agents into the matrix, into the metal matrix. During the reaction, intuitively, inside the melt, some reaction will happen. So intuitively, some compound will form. That compound is act as a reinforcement, that is called in situ compound. So again, we can classify composite into four different categories, that is particle reinforced composite, fiber reinforced composite, structural reinforced composite, and nano composite. So with respect to the reinforcement, we are classifying this. The particle reinforced, the first one is dispersion strengthened composite. That means nano size particle or submicron size particles we are adding to the metal matrix, and it will improve its strength property and other creep property with respect to its addition and the composition of the metal and the reinforcement. Again, the large particles, about more than 500 micrometer particle, if added to the metal, then we used to call it as large particle reinforced composite, metal matrix composite. The fiber composite we can classify in two categories. One is continuous aligned, another one is discontinuous aligned. Continuous aligned means entire the total product, the reinforcement will be there, and it is a continuous rod kind of thing. In the discontinuous type, like flake, aligned means discontinuous aligned and randomly oriented composites are there. The structural means it's a laminated type of composite. Mostly we used in the polymer-based composite, and some of the metal matrix composites also in laminated type and sandwich type of panel also there. It is nano composite. Nano composite means the particle size is nano size, means that we used to call it as nano composite. If you see any composite, the main factor is interface. How the reinforcement and the matrix is added together or bonded together. That is called interface. There is always an interface between the constituent phases in the composite material. For the composite to operate effectively, the phases must be bond where they join at the interface. So the first picture we can able to see, there is no specific interfaces are there, bondings are there. Directly it is bonded with the matrix. The reinforcement is bonded with matrix. The circle particle, the round particle is secondary particle, and the surrounding gray color is a matrix. So there is no interfaces. So sometimes we know there is no interface connection will be there. Now, by experience, we can understand. So that time we used to add some reactive agent to the matrix or reinforcement. Then we can make a third ingredient to bond the reinforcement and matrix. That is the different second type. And the third type is if you add some particle to the matrix, intuitively or by the reaction, some interfaces will form surround the particle. That is the third type of interface. So always the interface is a matter with respect to the interface strength, the interface bonding, the material property will vary. So we can compare the composite and metal by, you see, toughness, formability, joinability, corrosion resistance of the metal is high. So strength property is little low compared with the ceramic. So if you want to improve the strength property or high temperature withstanding property, we are adding ceramic particle to the metal, and we are altering the property into higher level as per our need. Now we can go for the metal processing. Metal processing is a manufacturing process used to shape metal into parts or end products. Generally, metal processing is from smelting to secondary processing. Generally, smelting, primary processing, and secondary processing is there. Now we can see in very important thing, alloying. So generally, pure metal will not give more strength. Pure metal is always in less strength, high ductility, and if you want to reach our requirement, means as per our performance, if you want to improve our property, we used to do alloying. Alloying is a process in which two or more metal elements are melted together in a precise combinations to form a specific material that is called alloy. Generally, we can do alloying in metal casting and powder metallurgy. So that we are going to see in this session. So first step is smelting and refining. Smelting and refining means iron ore or aluminum ore, or from ore to the ingot. From ore or scrap material, we melted it using blast furnace or cupola furnace. Then we are refining or smelting the from ore to the pure ingot level. That is called smelting level. This is the first step of metal processing. The second one is metal casting. This the first piece, and the first picture is this is the ingot. This ingot is come from ore to
Dr. Ajith,
yeah.
take your session.
Okay.
Thank you.
Thank you. So metal casting is a process in which hot liquid metal is poured into the mold or a cavity that contains a hollow cutout of a desired finish shape. The liquid metal is then left to solidify, which is removed from the mold, revealing the end product or casting form. These are the different casted product. Casting is one of the oldest type of metal fabrication technique. It is one of the most flexible method of metal fabrication to reach near net shape of complex shape matter. Good dimensional accuracy. Very large parts can be produced in one piece. Thin section also possible in metal casting. And other important metal processing technique is powder metallurgy. This is a solid state route. The metal casting is a liquid state or liquid kind processing. Powder metallurgy is a solid state processing method. In the process, we have metal powders or metal lumps or metal with the ceramic lumps to make composite. So first we used to mix using some ball milling or some mixing machine. We used to mix a sample powder. Then that powder we put it into the mold and we used to do compacting. After compacting, that part or sample is put through for sintering. After sintering, we can get the finished product. The powder metallurgy process involves mixing elemental or alloy powders, compacting the mixes into a type, then it is sintered or heated. The resultant shape is an atmosphere controlled furnace to metallurgically bonded particle. So advantages of powder metallurgy is virtually unlimited choice of alloys. So in the case of metal casting, we can't do that any metal. It's not possible because some refractory material, high melting materials like tungsten, tantalum, molybdenum, titanium, that melting temperature is about 3,420. So melting and casting is very difficult. So this kind of material, powder metallurgy is a best method to make a component or parts. Very good material utilization, near net shape is possible. Precision parts can be produced. Mass production also possible in powder metallurgy. So in the powder metallurgy process, one of the important steps to make alloy is means solid state alloying is ball milling. Ball milling is a grinding method that grinds particle or lumps into extremely fine powder. During the ball milling process, the collision between the tiny rigid balls in a concealed container will generate localized high pressure. So mechanical alloying. So we already discussed alloying. Alloying means mixing two metal elements and making a new alloy. So by liquid metallurgy, it's easy because in the liquid metal, liquid aluminum, if you put some cerium lump, it will immediately mix with aluminum. We can make aluminum cerium alloy or aluminum silicon alloy. But in the case of solid state, we are using ball milling. In the mechanical alloying method it's the solid state and powder processing techniques involving repeated cold welding, fracturing, and rewelding of blended powder particle in a high energy ball mill to produce a homogeneous material. This machine is available in our industry. We used to do grinding the geological materials like rocks, minerals, sands, stem of sediments and soils, iron ores, iron oxides, ferrite, brittle alloys, graphite, and all other metal metal powders we are using by this machine. These bowl and balls are made up of tungsten carbide. And the second one is secondary processing. After the primary processing like metal casting and powder metallurgy, then we go for secondary processing. There are n number of secondary processing is there in every category like forming, machining, joining, labeling, and mounting. So every secondary processing will alter or change the structure of the material. So if you see after secondary processing and before secondary processing, if you see the microstructure, it will vary. Atomic level also it will vary. So if you want to improve the property or change the shape, we used the secondary processing methods. Some of the category we can just by the heat treatment we can improve the property, we can improve the grain size, and these all of the methods come under secondary processing. So general secondary processing like forging, rolling, ECAP, extrusion, and drawings are there. By this method, we can improve its strength property by grain refining. And another one new method is additive manufacturing. The additive manufacturing is the process of joining material to make objects from three-dimensional model data, usually layer by layer. This is a 3D modeling. So here the liquid metal or generally we used for polymer material. We are in the general printing, we are printing it in 2 dimension and X and Y dimension. But in the case of 3D printing, we have in Z direction also. We are printing again and again in the top of the print, then we got the object like a 3D printed object. So in metals, we use that selective laser sintering. It's a process of laser sintering powder material at point in space defined by computer using 3D design. By the knob and heating system, we can change the knob using computer. We can make a compound, and it is with respect to its melting temperature of the material, which material we are using for that. And metal matrix composite processing. Earlier we discussed about what are the different types of metal matrix composite. Now how we are processing the metal matrix composite. There are 2 different methods are there. One is liquid state processing, another one is solid state processing. Liquid state processing comes stir casting, squeeze casting, spray casting, and solid state it is powder metallurgy and friction stir process and diffusion. This is a basics composite making method. Liquid state processing method. This is the stir casting thing. We have a crucible. In the crucible, we used to melt the material like aluminum, magnesium, any metal. We used to melt it above its melting temperature. Then we during the mechanical stirring, we put the stirrer with motor. Then it's about 100 to 1000 to 1500 rpm. If you stir it, we can get the vertex. In the vertex, if you put some ceramic particle, it will melt. Mix homogeneously, and some heterogeneous mixture will come into the picture. Then, if you pour into the mold, we can get the composite. And second one is infiltration. This is the infiltration method. For the infiltration method, we have some preforms, ceramic preform will be there. On the ceramic preform, we used to pour the liquid metal, and using press, if you press it, then all the liquid metal will infiltrate to the ceramic preform, then we can get the composite. Infiltration methods are there, that is squeeze casting. This is a squeeze infiltration. The green color is a preform, the red color is a molten metal. Then we used to press the liquid metal. During that pressing, infiltration will happen. This is called a squeeze infiltration. Again, one is gas pressure infiltration. Instead of press, we use gas. During this high pressure gas, high pressure nitrogen gas, or with respect to metal to metal, the gas will vary. If you give the pressurized gas to the container, due to that pressure, the liquid metal or molten metal will infiltrate into the preform, then we will get the composite. Again, another one is pressure dye infiltration. Component like that, the green color is component kind of things. If you want a component like a small gears or small parts like that, we used to fix the cavity. In the cavity, we used to fix the ceramic preform. In that preform, using the plunger, the molten metal will fill into the preform, then we will get the composite material. This is spray deposition technique. In the spray deposition techniques, one preform will be there. The liquid metal is sprayed on the preform. Due to the high pressure spray, the liquid metal spray will infiltrate into the preform. Then we can get the composite. Another thing is solid state processing. Earlier we discussed about the liquid state composite processing. Again, this is a solid state processing. This is already we discussed using the ball milling or mechanical alloying. We used to do this. That is aluminum and silicon carbide particle. If you have two different things, aluminum lumps or aluminum pieces with this silicon carbide particle, we will put both the things into the ball milling setup. Then we will mix it. It's about 1 hour, or with respect to its time, if you vary, we can get the mixed powders. After that, if you press or compacted after sintering, after heating, we will get the component. Then diffusion bonding. Diffusion bonding means one fibrous and one metal foil will be there. After that, if you press it, we will get the composite, because the liquid means metal will infiltrate into the fibers, then we will get the composite. Then friction stir processing. This is a selected area composite making process. This is a friction stir processing. One friction knob will be there. If you want a composite in a particular area, that means in the white region, if you need a composite, initially we used to take a groove. On the groove, we put the ceramic or any reinforcement particle we want to do. That particle we used to fill. After that, during this rotating knob, we will get friction stir processing. By this friction stir processing, we can make the composite in the particular area. And these are the composite microstructure of silicon carbide, aluminum, diamond copper, and carbon short fiber copper composite. These are the different microstructure of composites. So now we will go for light alloys. Light alloys. Why light alloys are important? What is the need of that? Like if you see, day by day increasing the fuel price, like petrol, diesel, gas price, and more vehicles are coming day by day. So due to that, more amount of CO2 emission is coming to the atmosphere. So to reduce the CO2 emission and to reduce the usage of fuel. One of the best way is reduce the vehicle weight. Weight reduction is one of the most important objective of aerospace and automobile industry. Every 10% of weight reduction in vehicle increase about 6 to 8% of fuel efficiency and corresponding reduction of about 17 to 20 kg of CO2 emissions per kg of weight reduction over a vehicle lifetime. 100 kg represent a fuel savings of about half liter per 100 kilogram for a vehicle. Minimizing every gram weight of components of a space shuttle is more significant. So if you see light elements into the periodic table, these all are the light elements like the lithium, potassium, sodium, rubidium, calcium, magnesium, like that. So we can't use all the light elements to make structural material. So some of the metals, some of the elements are metals. The light metals we used to call because it is low density. So low density metals are light metals. Developed these light metals developed in mid 19th century. Lithium, magnesium, beryllium, aluminum, titanium are most important light metals. So lithium, it is a highly reactive and flammable material, must be stored in mineral oil. Lithium reacts with water easily, and we can use this lithium, the rechargeable batteries for mobile laptops and the digital cameras and electric vehicles. And lithium oxide is used in special classes, heat resistant classes, and ceramics. Another one is beryllium. Beryllium is low density material. It's about 1278 degree melting temperature. So the temperature, high temperature withstanding capability in light material is high in beryllium. We can use this beryllium to aerospace and nuclear industry, satellite and antenna bombs, and heat sinks, thermal management properties, and the supersonic transport aircraft. We use beryllium because of its high temperature properties. And it is so costly to mine and extract low ductility at ambient temperature, extremely toxic. Again, we know that aluminum is the second most plentiful metallic element into the earth, and esteemed 8.3% of the earth crust is composed of aluminum. It is very soft, malleable, ductile. It is very good conductor for heat and electricity. It is a non-magnetic substance. So we know aluminum usage in every day. We are using aluminum. Application of aluminum is numerous. Most of the aluminums are used in construction, ranging from aluminum foil to foil for food packing to the structural members in the aircraft in which we travel. So that much huge area we are using aluminum. Again, the titanium. Titanium is the strongest and most durable metals on the planet. Titanium has highest strength to density ratio of any metallic elements on the periodic table. Titanium alloys is used in aircraft, ships, spacecraft, missile, and in steel alloys to reduce grain size. And as a deoxidizer, we are using titanium. And that limitation is difficult to casting. Unlike iron or aluminum, we can easily cast, but in titanium, the casting is very difficult and it's more expensive. So in between, magnesium will come. Magnesium is the density is 1.74. If you see all the structural material, not only light metal, all the structural metals, magnesium is the lowest density structural material. It is about 1.74 gram per cc. And in the earth crust, the abundant element in the earth crust, if you see, it is in the 8th position. It's about 2.74% of magnesium is composed into the earth crust. And if you think about its specific stiffness and the specific strength, the property is high in magnesium. That means high specific strength and specific stiffness. More than that, it's a superior damping property, excellent castability, highly recyclable, good machinability, good weldability under inert atmosphere. So application of magnesium is nowadays it's very vast. Most of the automobile parts, automobile devices we are using magnesium. About 70.8% of magnesium we are using in automobile sector, and sporting good, power tools, industrial machinery, energy equipment, computer and electronic products, and other products we are using magnesium. And in recent high-end cars, we are using magnesium. About 10 kg to 80 kg of magnesium we are using, and day by day the magnesium research is vast, and you can see in Chevrolet, Volkswagen, Acura, and Ford, all the cars they are ready to use magnesium because of its lightweight and higher strength to weight ratio. And if you see the literature, day by day, the magnesium research is coming in good position. That means year by year, you can see it's in 2018, about 2,768 journals are coming into the core magnesium area. Lot of research is nowadays coming in magnesium-based alloys and magnesium-based composite. We can classify magnesium alloys into two different categories, that is aluminum-containing magnesium alloy and aluminum-free magnesium alloys. So we used to the composition, with respect to composition, we used to put coding in magnesium alloys, that is AZ91. AZ91 means 9% of aluminum and 1% of zinc into the magnesium. That is AZ91 magnesium alloy. So every coding is like that. AE42 means 4% aluminum and 2% rare earth. That is AE42. So then we will come into material characterization. In this material characterization session, we discussed material characterization with the real research data. So for better understanding, I am going to show you about some PhD research, the thesis data, and some of the papers data. So after the processing, that means after metal processing, like metal casting or powder metallurgy or any like a 3D printing, the first characterization technique is XRD. So from the XRD, what are the different phases present into the metal that we can get? So from the XRD, not only that, we can distinguish between crystalline and amorphous material, determine the structure of crystalline material, determination of electron distribution within the atom and throughout the unit cell, to measure the thickness of thin films and multi-layers, determination of the orientation of single crystal, determination of the texture of polygrained materials, measurement of strain and small grains, etc., that we can able to see using XRD. This is a typical picture taken from our thesis, that is with respect to the silicon addition, how the XRD is changing. You can see we are adding silicon lumps to the magnesium melt. Then we are mixing it, holding it, and pour into the mold. We got magnesium silicon alloys. But the XRD, there is no silicon peaks are there. All the silicon are mixed with the magnesium, and we got Mg2Si phases. So with respect to the silicon addition, the intensity height is high. So intensity value is changing with respect to the silicon addition because more amount of Mg2Si is present into the particular material. That means in magnesium 10Si, the Mg2Si phase percentage is high. So the intensity value we are getting more. So not only that, what are the phases present in the particular material that we can identify using XRD. Second one is chemical analysis. What is the composition of particular metal piece that we can get it or we can understand or analyze from chemical analysis. That is wet chemical analysis. Wet chemical analysis we can classify into qualitative chemical analysis and quantitative chemical analysis. Then optical emission spectroscopy. From the optical emission spectroscopy, we can get bulk elemental analysis. So if you make by casting aluminum, magnesium, strontium, Silicon alloy means what is the composition, what the final composition we reach, that we can check using optical emission spectroscopy and inductively coupled plasma spectroscopy. Microscopy. This microscopy is a category of characterization technique which probe or map of surface and subsurface structure of the material. These are the different microscopes that are optical microscope, scanning electron microscopes, transmission electron microscope, atomic force microscope, like that. The first one is optical microscope. So it is easily available. We can see the entire structure and phase difference using this optical microscope. Optical microscope is a light microscope, like light method. We are that is the mechanism of this light microscope or optical microscope. There are some lenses is there. The AB is sample, means that focusing area. By using this focal length variation, we can get A dash B dash. That means magnified image using this optical. Images we are taken from we have this optical microscope, Olympus optical microscope in our industry. These are the samples, different samples. Someone is aluminum, zinc, tin, and silicon based alloy, and aluminum, magnesium, zinc alloys are there, magnesium tin alloy is there, and laser welded. This microstructure is a laser welded microstructure, and frictionless strip casting microstructure. This is the weathering steel microstructure. This is a coated, means on electrode is coated using zinc and titanium. That kind of coating samples also we can see the microstructure clearly. And for microstructure, we need to do polishing, because we already discussed that this is a light microscopy. By the reflecting light only we are getting the microstructure. So we need like mirror type of polishing. So for mirror type of polishing, we need to do polishing using this polishing machine. This polishing and mounting machine is available in our industry. If in case if we have very small like pin or lumps, like bold type of samples, it is very difficult to hold and polish. So in that condition, we use mounting machine. So after mounting, you can see in the bottom picture, this is after mounting, the samples look like this. And another one is scanning electron microscope. In the case of optical microstructure, we can able to see it's about 5x to 150x magnification. So if you want to more magnification, if you want to see a nano or submicron kind of particle, we need to go for other microscopes like scanning electron microscope or transmission electron microscope. From the scanning electron microscope, we can see from 5 to X magnification to provide you with high quality depth of field images. Semi-micrography is an effective tool in failure analysis, contaminant analysis, and general microanalysis. That is, failure analysis means after fracture or after pre-fracture, after fatigue fracture, we can analyze the fractured surface using SEM. What kind of fracture? It is a brittle fracture or ductile fracture, that we can understand from the scanning electron microscope. So irregular shaped surface, like after wear testing, one sample will be there. That one sample, if you see how the structure is, then we can understand what is the mechanism of its wear. Then transmission electron microscopy. Transmission electron microscopy is the most powerful microscope. TEM microscope is a technique in which a beam of electron is transmitted through a specimen to form an image. So in nanometer scale or lattice level, we can see that. So application of TEM. The 4 different application is there: conventional TEM, in situ TEM, analytical TEM, and HRTEM. Conventional TEM means for nano-sized microstructure and morphology. This small grain size, nano grain size is there, or orientation we can see using the conventional TEM in nano scale. And in situ TEM means during the TEM experiment, we can see the deformation. We can see the environment, means corrosion, intuitively we can see the video. And phase transformation, during heating, if you take TM, institute TM, then we can get the phase transformation video. Then another one is analytical TM. We have a picture, means in TM image, some dots or some needle kind of structure is there, means what that phase contains. That we can check using the analytical TM. It will show the composition. And another one is HRTM. From the HRTM, we can understand lattice imaging, structure of the complex material, and atomic structure of the defect that we can able to see. These are the microstructure. This data is taken from my thesis. It is magnesium silicon alloy. With respect to silicon content, how the microstructure is changing. This is 0.5% silicon and 0.7%, 1.15% silicon. So you see, the white region is the alpha Mg. So initially we can able to see the two region only. One is white region and one is gray region. So the white region is changing with respect to silicon. That white region is called dendritic kind of structure. This is look like a dendritic kind of structure. With the increasing the addition of silicon, the dendritic structure is reducing. At the same time, in the interdendritic region, some gray phases are coming. So this in 1.15 SA, the gray region is more. Then we analyzed using SCM analysis. You see, this gray region is a lamellar kind of structure. So it's like a needle kind of structures are there. So this is the lamellar spacing. We analyze that. So from the high magnification system, we can understand how the eutectic phase is formed. After that, we understand how it is formed, how the microstructure is forming during solidification. That we can discuss using, we can see using this phase diagram. This is a partial phase diagram from 0 to 1.34. 1.34 is a eutectic point of the magnesium silicon system. So if you solidify from the liquid melt from 720 degrees centigrade, if you melt, the melt temperature is 720 degree, then continuously we are reducing its temperature or switch off its furnace. Then if you see, when it reaches 650, 650 is the melting temperature of magnesium. When it reaches 646.21 degrees centigrade, that means 0.5% silicon, it starts solidification. Initially, the alpha Mg will solidify, the remaining are liquid. Then the alpha Mg will grow like a dendritic kind of structure that we can see here. So in the interdendritic region, this is the interdendritic region. During the growth, because the solubility of silicon in magnesium is very less, that is 0.02%. So it will reject the silicon atom out of the dendrite. So in the interdendritic region, the silicon phase is rich and our silicon element is rich. When it reaches to 637 degree temperature, immediately the lamellar kind of eutectic will form. This is called eutectic structure. This eutectic is forming, we already see the picture, this lamellar structure. This lamellar is formed because one MGTSA phase line will form. The surrounded the MGTSA phase line, the silicon content or silicon atoms are minimum. So in between that region, alpha Mg will form. So this is called the coupled eutectic growth. This is hypereutectic. Hypereutectic means above the eutectic point we used to call this is hypereutectic. Below the eutectic point it is hypoeutectic. This is above the eutectic point. Mg2SA, Mg6SA, Mg8SA and Mg10SA. With respect to the silicon addition, the morphological changes we can able to see. So in case of magnesium 10SA, the primary, the one new phases is there. Earlier 2 phases are there. Now 3 phases are there. One is black color phase and surrounding one white color region and one gray region. Then we checked it using SEM, scanning electron microscope. You see that the black color region is primary Mg2Si that we understand using SEM IDAX analysis. That means point IDAX analysis. From the point, it is 65.73 atomic percentage magnesium and 34.27 atomic percentage silicon. That means 2:1 magnesium and silicon there. So we are calling it Mg2Si. So this phase is Mg2Si. It is confirmed using SEM microscope and IDAS analysis. Then again you can see after that white region in the microstructure, some different phases are there. The high magnification SEM picture we can able to see here. It's look like a Chinese script. So we used to call this structure is Chinese script structure. This is a eutectic microstructure. So these all of the structure is forming during the solidification, and we can see now how the during solidification the structure changes is coming. In 6% silicon addition, when it you can see we can assume the melt temperature is about 800 degree or 850 degree. After melting, when you started solidifying at 794.47 degree, the first part is Mg2Si. That means primary Mg2Si will start. Then step by step it will grow like a polygonal type of structure. Then surround that means it is taking silicon from the outer region. So the surrounded region is silicon free region. So surrounded region, when it reaches 657.8 degree temperature, immediately alpha Mg will form. Remaining will be in liquid condition. When it reaches 637 degrees centigrade, immediately that eutectic Mg2Si will form like a Chinese script or needle kind of structure that we discussed in this SEM microcosm. Now, after this understanding, after this analysis, we understand that there are two different kind of structure. One is hypoeutectic structure and hypereutectic structure. In the hypoeutectic structure, one lamellar kind of alpha Mg and eutectic kind of, that means line by line kind of Mg2Si structure. Mg2Si eutectic structure is there. In the case of hypereutectic, there are three different structures there. One is primary Mg2Si, and white region is alpha Mg, and this is Chinese script eutectic Mg2Si. So this coarse morphology is the reason for reducing its properties. Because of it, this coarse morphology, the tensile property is reducing. So if we modify this property, we can improve the property. From the literature, we can understand that there are different modification methods are there, like hot extrusion, reciprocating extrusion, rapid solidification, mechanical alloying, solution heat treatment, semi-solid material processing, melt superheating, electromagnetic vibration, and modification by alloying elements. These are the different modification method of magnesium silicon alloys to modify the structure. Then by the modification, we can improve the mechanical property or other property. So one of the important modification method is modification by alloying elements. So in our thesis, we did we choose 4 different elements like mismetal, neodymium, calcium, and strontium. So we check these 4 elements into 2 different alloys. That is, one is magnesium 1.15 Si alloy and another one is magnesium 6 Si alloy. So by the addition of these elements, how the microstructural changes is coming, what is the reason that we analyzed? I'm just showing only one addition, that is neodymium addition. The addition of neodymium, you can see the coarse lamellar structure changes to the discontinuous lamellar structure in 0.3 ND, 0.6 ND. So with the different addition, you can see that variation in microstructure. And in the high magnification views, that means if you see the lamellar eutectic structure, now the lamellar space is very less, and when you go for 0.9% ND, addition of ND, there is no lamellar or line kind of structure. All the structure are look like particle kind of structure. So when it reached 1.2% ND addition, there we got some star kind of compound into the MatRICS or in interdendritic region. So that we analyzed using SE. SEM it does. This analysis is called SEM mapping. From the SEM mapping, we can understand that you see here that this area is magnesium free. There is not much magnesium is there, and the white region, this portion silicon is there and Nd is there. So from that analysis, we can understand that this phase is Nd silicon pieces, and by point analysis and point index analysis, we understood that that phase is Nd Si2 phase. And with respect to the addition of neodymium, the property is varying, and this is the fractograph of the before modification, means unmodified and modified alloy fractograph. And how the modification happened, that we can discuss, because in the initial stage, all in the crude container or the mold, all liquid or in liquid, all metal or in liquid state. And when it starts solidifying, initially some nucleon will be there. That nucleon will grow together and it will form a dendritic kind of structure. So we need some nucleons. So when we add some alloying elements like neodymium, nucleons number of nucleons are high. So simultaneously, at the same time, more dendritic alpha Mg will grow all the places. So there are more interdendritic regions will be there. So in between the interdendritic region, this eutectic Mg2Si will form. So when we add 1.2%, that means more neodymium. That neodymium itself form a compound, or that means NdSi2. Then it will not give any modification effect that we used to call over modified alloy. In the same time, how the needle kind of, how the Chinese script kind of structure or the laminar kind of structure is coming to the dot type of structure, means how the modification happened means this is due to the poisoning effect and impurity induced tuning mechanism, because during the solidification, during the eutectic solidification, this red atom is neodymium atom. This atom will restrict the growth and it will make the discontinuity of the. So these are the, with respect to different element addition, you can see different microstructure. So with respect to its microstructure, the tensile property is also varying. And this is the alpha Mg dendritic growth morphology changes, and another one is there are two different structures there. One is primary Mg2Si structure and another one is eutectic Mg2Si structure. These both sides, left and right sides, are after modification. This is the modification of primary Mg2Si. This is the refinement of eutectic Mg2Si. This Chinese script structure is modified to dot or needle kind of structure into the picture that we can able to see. These are the SEM images. So we can analyze by like this way. Then we can go for mechanical testing. In the mechanical testing side, harness, tensile, compressive, fatigue, creep, toughness, and the torsional behaviors are there. First, we will see harness testing. Harness is measure of material resistant to localized plastic deformation such as dent or scratch. So different type of harness is there: Brinell harness, Vickers harness, Noob harness, and Rockwell harness. With respect to the probe or indentation mark, we can classify this different category. And there are three different harness testings are there. That is macro harness, micro harness, and nano harness. Macro harness means that is we can be able to see the indentation by naked eye. That is macro harness. And the micro harness means we can check the harness of particular phase. One phase size is about 100 micrometer size, means we can able to see the particular phase harness. Means in a material, three different phases are there, means we can able to identify what is the harness of three different phases. Again, nano harness. If you want to check the harness of submicron size particle or nano particle, we can use nano harness testing machine. So this is the example of that. You see, with respect to the silicon addition, harness value is increasing. And if you see the micro harness, alpha Mg microharness is very low. It's about 36 or 37 HV Vickers harness. But in the case of primary Mg, this is same alloy. That means same microstructure. We are taking different harness. So different places we are indenting. Same metal, same places, same surface, different places we are indenting. The first place is alpha Mg place. In the alpha Mg place, if you see the harness is about 37 HV. Then in the eutectic region, it is about 58 to 70, that range. Then if you check the primary MG2SA, check on the harness of primary MG2SA, you can see like a polygonal kind of the indentation mark. That all the corner, we can able to see some cracks are there. This is due to the this material is highly brittle material. Due to that brittleness, when you indent on the particular face, it is cracking like glass. So from this analysis, we can understand that due to the indentation mark, the breaking is happening. This is because of high brittle M2TSA particle is there. So if you if you increase the M2TSA phases in the particular material, the property will always reduce. So always the metal the polygonal shape M2TSA will be small. Then only we can improve the strength property. Then tensile testing. Tensile testing, from the tensile test, we can understand ultimate tensile strength, breaking strength, maximum elongation and reduction area, that we can able to understand. These are the tensile testing samples. We are making tensile testing samples also in our laboratory. From this tensile value, we can get the Young's modulus, Poisson ratio, yield strength, and strain hardening capacity. Creep is a plastic deformation of the metal occurs as a function of time at a constant load or stress. So creep is a time-dependent process where a material under a applied stress exhibits a dimensional change at high temperature. The process is also temperature dependent. Creep always increases with the temperature. Again, is a fatigue testing. Damage or failure of the material under long period of cyclic load is called fatigue testing. The fatigue mainly occurs in structures subjected to dynamic and fluctuation loads. Fatigue failures comprise 90% of all metallic failures. So different types of fatigues are there: mechanical fatigue, creep fatigue, thermomechanical fatigue, corrosion fatigue, and fretting fatigue. So three stages are there in fatigue analysis. There is initial fatigue damage, progressive cyclic growth, and final sudden fracture. The first one is initial fatigue damage, leading to crack nucleation and crack initiation. That is initial fatigue damage. Progressive cyclic growth of crack, until the remaining uncracked cross-section of the part becomes too weak to withstand the load applied. And then the final stage is sudden fracture of the remaining cross-section will happen. That is final sudden fracture. So we can see with the example, the tensile property. You see, with respect to the silicon addition, 2 to 4% we can see we are getting good property, good mechanical property. Then we analyze that fracture sample. That means fracture tensile samples using SEM. From SEM analysis, we understood that this is a cleavage kind of ribbon patterns are there, and you see magnesium 6SA, the particle breakage is there. The primary M2TSA breakage we can able to understand using this SEM analysis, and in case of magnesium 10SA, very long particle breakage we can able to see. So the reduction in tensile property is due to the brittle M2TSA particle present into the microstructure or present into the particular material. Due to that, the failure is happening. Then we studied the evaluated temperature tensile behavior. In the evaluated temperature also, we are getting 2 to 4% silicon is showing good property, and we again analyze the fractogram. That means how the fracture happened. Higher silicon content alloy, that means 6 to 10% shows better yield strength. Primary M2TSA dendritic debonding and breakage is observed. that we can able to see in magnesium 10 the dendritic kind of breakage we can able to identify. The yield strength remains same when even at the elevated temperature in high silicon alloys. So we can correlate this tensile property with the fracture analysis. So fracture studies. So what is the reason for the tensile changes that we can identify using this SEM images? This is the compressive properties. With respect to the silicon addition, the compressive property is going high. The small image is there. This is a sample after failure. In pure MgA, the compressed effect is high. In case of magnesium 10 there is no compression. The sudden breakage is there, but it is withstanding more compressive load. Even though after that immediately sudden load, sudden breakage is there. There is not much ductility is there that we can able to identify. So after that compressive testing, we did SEM analysis. From that SEM analysis, you can see this is a shear bands. In pure MgA, the shear bands are very large. When you add magnesium 1.15 SA, the minimum small shear bands are there. In magnesium 10 SA, because of primary MG2 SA, more number of primary MG2 SA, the shear bands are more. So it is immediately breaking, but it is showing more compressive property. Then we can go for tensile property, tribological property. This is a tribological samples, 6 mm diameter to 12 mm diameter samples we can use. The length is about 26 mm length samples. This is pin on disc we are testing setup. From that pin on disc we are testing setup, we can get the data of height loss, sliding distance, and frictional forces. So from this data, we are analyzing how the wear property is changing. You see, in every wear, the sliding distance and wear volume, if you see the graph, initially A to B is a transition wear, and after that B to C is a steady state wear. Always we used to take steady state wear for further analysis. In the steady state wear region data, we take for further analysis like height loss plus time. From the height loss plus time graph, we can get the slope value of wear rate. So wear rate is the volume loss per sliding distance. So with respect to the silicon addition, the wear rate is reducing, wear resistance is increasing. Then we can make a graph of specific wear rate, wear coefficient, and coefficient of friction value that we can calculate using that data. So after that testing, we analyze the SEM of all the samples, all the wear samples and the own surface and wear debris. These are the wear debris of different samples. These are the own surface of different samples. From that, we can understand that this pure energy, the deep grooves are there. That is due to the thermal softening and melting. This mechanism is thermal softening and melting. And in magnesium 1.15 SA and 6 SA, you see there are like delaminated type of spaces are there. And in the same time, if you see in the debris also look like a delaminated kind of particle. So we understood that this kind of wear is delamination wear. And in case of magnesium 10 SA, there is very small tiny particles are there. And if you see the SEM image, that line scratches are very small. Because of hard MG2 particle present into the matrix, it is not, we are not able to make a deep groove. That's why very small scratches are there, because it is barring. That MG2 is act as a barrier for wear. So that we can confirm using wear debris. So with this talk, we understood that. So every microstructure, every secondary processing is changing its microstructure. So if you do some ECAP or pressing extrusion, the microstructure value will change. With respect to the microstructure, we can alter the properties of the particular material. and always how we are processing. Is it is processed by 3D printing, or it is processed by metal casting or steel casting or powder metallurgy. So with respect to that, the microstructure will change. So with respect to this microstructure, we can alter the property. So every time engineer used to check the property, and with respect to what performance he is expecting, and for that performance, what is the range of property that is necessary. That property is always related to the structure of the material. That structure we already discussed, that is depends upon its microstructure or macro structure or atomic structure of the particular material. So this we can conclude. These are the facilities available in our MatRICS lab. This MatRICS lab is made for young researchers and students doing Ph.D, ME, and B.Tech program. And it is very difficult to do casting or other analysis in the industry because their regular processing will be there. But in this industry, it's mainly focused, and it is helping for young researchers and scientists. Not only in Tamil Nadu, all over the India, we are focusing the people. We used to alter the structure or alter the mission and make the samples or make the experiment for students. These all are the material we are dealing with. We are selling these all are the material: magnesium, aluminum, zinc, silicon, lead, tin, selenium, and not only that, rare material like cerium, praseodymium, yttrium, gadolinium. These are the samples, but generally in a big industry they won't sell in gram size, but we are giving for researchers in gram size also. What is the necessary quantity we are giving. And the master alloy like magnesium, aluminum master alloy, and ceramic powder like silicon carbide, black silicon carbide, boron carbide, titanium carbide, tungsten carbide, and all the master alloys. Not only master alloys, if you design the alloy and you want to make any alloy, we are making. Not only alloy and composite we are making for researchers. Thank you very much. Thank you for the opportunity.
Thank you, sir. Dr. Ajith, very wonderful presentation. I never watched this kind of presentation in any webinar and seminar I attended. The presentation are good. The continuity of slides, image shown in the PPT are clear, and your explanation about the topic are very neat and informative. Thanks for your effective support for this webinar.
Thank you.
Dr. Ajith Kumar, our participants also give a very good feedback in our comment box. Now I'm going to ask a few questions. These questions are asked from our participants. Are you ready, Mr. Ajith?
Yeah, sure.
Okay. The first question, name of the softwares which is convert data into graph while studying characterization, studying material characterization by Abdul Salam.
No, actually the question is not clear. Please repeat it once again.
Okay. Name of the softwares which converts data into graph while studying material characterization.
So he is asking from means from graph to software data.
Converting data to graph.
Okay. Generally, we used to do Excel and some softwares are there. Presently, I forget the name. If you mail, I will give 3 or 4 softwares are there to make these graphs.
Okay. Okay.
Okay.
Wait a minute. Other question from Vishwanath.
Okay.
Any safety aspects to be followed as magnesium is involved?
Yeah, always safety is necessary because it will easily fire during casting. When you cast magnesium, we need to do what protective flux or protective gas atmosphere only we can able to cast it, and we should use all the safety devices before casting or during casting. We use all the safety devices. Then only it is perfectly safe. And it always try to fire. So to avoid firing, the protective gas atmosphere is necessary.
Okay, thank you. So another question from Abdul Asif. Which MMC used in aircraft industry?
No, all the MMC with respect to the application, all the MMCs are used in aircraft application like aluminum matrix composites, aluminum magnesium matrix composites are using. But which place we are opting or which place we are choosing with respect to that, the application will vary. But then with respect to that MMC will vary, and the composition and the percentage, all the thing will vary.
Okay, thank you. Another question from Malik. Any materials management software freely available?
No, actually, I don't know.
Okay, thank you, Ajit. Many questions from participants.
Okay.
So I will chat you privately.
Okay.
After complete the question, we will send them to mail or WhatsApp.
Yeah, sure.
Okay, thanks, Mr. Ajit. Now I call Mr. Sanju Vishal to present a vote of thanks. Sanju Vishal?
Sir, I'm here.
Okay, continue.
Good evening to one and all. Respected and most distinguished chief guest of the day, Dr. K.K.Ajith Kumar. Respected Principal Dr. V. Nagarajan, our beloved HOD Dr. M. Muthukumaran, and dear participants. Honored to propose the vote of thanks to all who have helped us in making this webinar such a resounding success. I, on behalf of Mechanical Engineering Department, extend a very hearty vote of thanks to our honorable chief guest who blessed us with his presence and took a valuable time in his busy schedule. Thank you, sir. A big thank you for Dr. K.K.Ajith Kumar for his sincere efforts to this webinar. I would like to extend the special thanks to our chief guest for inspiring us too. Now we all well known about significance of metal processing and characterization through your seminar. I thank you again, sir, for your informative speech.
Thank you.
I would like to express a profound gratitude to our principal, Dr. V. Nagarajan, for providing this encouragement and support for this event. I would like to thank our beloved HOD, Dr. M. Muthukumaran, for his moral support and guidance. I am happy to express vote of thanks to Mr. M. Krishna Kumar, Assistant Professor, Mechanical Engineering, Dr. Mahendran, Associate Professor, Electrical and Electronics Engineering, and Mr. Rajkumar, System Admin, and faculties who have made this seminar a grand success with your presence. Last but not least, I thank you all the participants for cooperation in making this event a great success. Once again, I thank you all for this cordial cooperation. Thank you. Thank you very much.
Thank you.
Thank you, Mr. Ajit. We can end our meeting.
Yeah, I can leave.
Thank you. Thank you, Doctor.
Thank you. Thank you so much.